Well, we're just cruising through this.
I was telling Dad about the one character. Yeah. She said, "What did it say?" And I said, "I don't know it." Well, I want to know what it said. Well, it's still there tomorrow.
All right. Get this going here. Yeah. All right. There we go. It looks like we're live. Call one person out, Rebecca, for not being here. His IT called me and said they wanted me to try something with her because she's having a hard time saving. So if she's listening, we need to try something. Because they said if it doesn't work, have her email. Okay. Anyways, how'd the exam go? Kind of looked at the first part. Simple, easy. I'm just finishing up the ecology exams to get up. There she is. There she is. I'm going to start going through the actual R stuff, the application part. That actually takes me a little bit of time because Blackboard is slow. It's like easy 5 to 10 seconds just to go from one exam to the next. It's just a pain in the butt. All right, so we'll get those done. Meantime, we are moving forward. So we introduced this standard error. Remember, I give you this function. This function does a lot of cool stuff, which is automatically remove missing data. So we don't have to do the na.rm and the standard deviation function. We don't have to do it in the length function, anything. It handles everything for us. Standard error is going to be the preferred method of reporting error. All right, and we're gonna basically it's a preferred method because we're almost always going to be doing some sort of statistical comparison, so we can report it as the mean plus or minus the standard error, or we can give the mean in the text and then report standard error in parentheses. If you have the means in like a figure, the mean and the standard error in the figure, just make sure that your figure legends specify what those error bars are. Either 95% confidence intervals or standard errors or 2 times standard errors. Just need to specify what those figures are showing. All right, so this leads to our confidence limits. All right, so confidence limit is basically generating some interval which is telling us how likely we are to actually capture that true value. All right, so we're kind of getting closer to hypothesis testing at this point. All right, what we have is a single parameter, population parameter, and then we collect a sample to try to approximate that parameter. Well, that sample, from that sample, we can generate a confidence interval. Hopefully, our sample estimate, say x bar, is equal to that population parameter mu. In which case, that's great. That's our ideal situation. But a lot of times, we're not equal to that. Our sample mean is going to be higher, it's going to be lower, which is why we report these measures of dispersion to kind of say, hey, our true value is going to be captured in some percentage of time. All right, so confidence interval is defined as the interval that is expected to capture the population parameter with a probability 1 minus alpha. So this 1 minus alpha is just going to be our percentage. So it can be a 95% confidence interval, in which case it's 95% likely that our interval captures that true population parameter. If it's a 99% confidence interval, 99% likely that our interval captures that population parameter. All right. Now our interval is going to have upper and lower values to it. All right. So for example, we can report the average plus or minus 1.5 if we're reporting a confidence interval, so that our confidence interval is 1.5 units below the average, 1.5 units above the average. That range itself is going to be expected to capture that true value a certain percentage of time. Now note the actual phrases expected to capture. We didn't say that our true value is going to fall inside of this interval a certain percentage of time. Because if we say that it falls within that interval, it implies that our population parameter can change, and it can't. Our population parameter is fixed. What changes is our estimate, is our x bar, our sample statistics. That's what changes. So it's very specific that we're saying this interval can capture our true value a certain percentage of time. And so our true value, if it's right in the middle, if I'm our true value, our interval could be like this. Next time we sample, it could be shifted over, but 95% of our intervals are going to capture that true value. It's a very important way to say it. All right, so here's the example. Let's say we have 5.7, or I'm sorry, 5 plus or minus 2, which gives us a confidence interval of 3 to 7. All right, we say that if we repeat our sampling over and over and over again, whatever percentage this interval represents, that's how many of these intervals are going to actually capture the true value. 5% of the time we don't. That's the alpha. That's the alpha. All right? And I do go over the incorrect. We don't say we have a 95% chance that the true mean falls within the confidence interval. That doesn't fly. Our true mean doesn't change. It's a fixed point. What changes is our intervals. What changes is our interval. All right? So how do we get it? How do we calculate these confidence intervals? Well, we calculate it using these equations. This down, confidence intervals of the mean. All right? So we have our mean, and it's going to be plus or minus a t-value. Cursive, there it is. A t-value times our standard error. And this will be our x, the sample mean, plus or minus some value t times the standard error of our sample, standard error of our mean. All right, so standard error is just our standard deviation over the square root of our sample size. Where do we get the t-value? Well, the t is a critical value from a t distribution. All right, it's a critical value from a t table. Critical value, where degrees of freedom is our sample size minus 1. So what is the t distribution? Well, t distribution is another continuous distribution. We've already learned about our normal distribution. All right. So recall that when we were doing normal distributions, we applied this transformation. X bar minus mu over sigma. What did that give us? What did that give us? What important variable did that give us? Anybody? You had to calculate it. Well, actually you didn't, because you let R calculate it for you. If you did it by hand, what would you calculate? What does that give us? Yeah, that's z-score. That's z, right? And the z follows a normal 0, 1 distribution. Now, note what we're doing. We subtracted the population mean and we divided by the population standard deviation. We might not know what the population standard deviation is. So what we do is we estimate it, we approximate it using the standard error of the mean, the standard error from our sample. Now, when we do this approximation now, when we do x bar minus the population parameter divided by the standard error of the mean, this does not give us a z-score because this transformation does not follow a normal distribution anymore. It actually follows a t-distribution. And the distribution, t-distribution, is going to be defined by the degrees of freedom, which by definition is going to be our sample size minus 1. So this curve shows you the distributions. The black line right here, curve d norm, -3 to 3. All right. So this black line is the normal distribution. That's what it is. All right. The red line is a t-distribution with 1 degree of freedom. You can see that it is not normally distributed. It does not follow the normal distribution. It is a separate probability distribution. As we increase our degrees of freedom, we do get closer to our normal distribution, but we're not exact until we get to a large degrees of freedom. We still follow a t, but eventually our degrees of freedom get so large, our sample size gets so large that we can approximate, we can utilize the normal distribution. Or we can utilize the normal distribution as an approximation. Now, where did this come about? How did we get it? All right, well, it's actually called a student's t-distribution because the guy that came up with it was actually W.S. Gossett of the Guinness Brewery. You've all heard of the Guinness Brewery, right? Right, some of you. Where is it? Ireland. Ireland, right? Dublin, right? What do they make? Dr. Pepper, right? Dr. Pepper, yeah. Dr. Pepper's imported. That's why Dr. Pepper is so expensive. Yeah. That's why you go for Dr. Thunder. Yeah. Is that the H-E-B brand or is that the Kroger brand? No. So the Guinness Brewery, all right, makes Guinness Stout. They actually make other beers as well. But W.S. Gossett was into statistics, all right, and one of the things that he couldn't do was publish papers under his own name. So the paper where he described the t-distribution, described how this follows this completely separate distribution, he wrote under the pen name A student, which then became known as student's t-distribution. So actually it wasn't student at all, it was W.S. Gossett. All right, so what do we know about this t-distribution? We know that it is symmetric. All right, it's symmetric. Percent, so mirror image. Left half is a mirror image of the right half, which is useful because if we do area under the curve, we only need one side, and then we already have the other side. All right. Our distribution runs from -infinity to +infinity. Same thing with the normal distribution. Where we differ from the normal distribution is that the shape of this curve depends on the degrees of freedom. All right, and our degrees of freedom is going to be the same as the denominator of the standard deviation, which is n-1. All right, so we're going to lose 1 degree of freedom from our sample size. That's our degree of freedom, sample size -1. And I demonstrate that change in shape right here, where you can see that as we increase our sample size, we get closer and closer and closer to our normal curve. Right. degrees of freedom will be n minus 1. Now, how do we get this value? Well, we can get the value in R pretty easily. All right, in R, we're going to use QT. So this goes back to our functions. R, right, is randomized. P is percentile or proportion. That's our area under the curves. All right. A D is a density that gives us the height of the curve for our continuous distributions. And now Q gives us a quantile, right, or gives us the quantile or vector of quantiles. All right. So if we were interested in trying to figure out the t values that correspond to a certain quantile value, we use QT. All right? And this is for the t distribution. If we were curious about the percentages or what the cutoff values are for a normal, we'd use Q norm. If we were interested in the cutoff values for a binomial, we'd use Q binomial. All right? That's how it works. So for us, we give it QT, we give it Q, the quantile or the vector of quantiles that we want. Normally, we're going to want 0.0275 or 0.025 and 0.975 because this area gives us 95% of the values between it and then 5% in our tails, 2.5% in each tail. Normally, that's what we're going to go for. But if we wanted a 99%, we would use 0.05, 0.005, and 0.995 because that gives us 99% in the middle, 1% in our tails. We have to give it the degrees of freedom. That's required. Our t distribution is defined by our degrees of freedom. And then we have to say lower dot tail equals t or f. All right. Normally for this, we're going to use lower dot tail equals true because it's going to give us the lower cutoff. So the 0.025 is the lower part of our curve. That's this spot. All right. And then the 0.975 says to the left of our line here, move this image. So to the left of our line at the 0.975 represents 97.5% of our points. All right. So this is how we would do 95% up here. QTC parentheses. All right. So in R, go ahead and do 95. Do a 90%, 95%, and a 99% using the QT function. While you do that, I'm going to open up my RStudio. Get that going. And Rebecca, before you leave, we've got a couple of things to try for IT. Degrees of freedom, let's do, I don't know, 5 degrees of freedom. We'll just arbitrarily say 5 degrees of freedom. are you doing? You get it? Get it? All right, real quick. Our confidence intervals, what they're doing is trying to capture the bulk of our values in this part of our distribution. So if we did a 50% confidence interval, we want to capture the 50% of all of the values, which would probably be maybe from 0.68 to 0.68 or so. All right, we're capturing the peak. As our confidence intervals increase, we're getting more and more. Our cutoffs are getting larger and larger and larger. The part that's in the tails would represent our alpha part of it. All right. So here's mine. So I went ahead and added a few more spots, a few more descriptions here. So we left off with standard errors, right? Now we're going to do our confidence intervals, all right? So with confidence intervals, we're working with the t distribution. That's what we need. We're going to do our cutoff, our t cutoff times the standard error, all right? And we're going to use the qt function to do that. All right, so for the 95% cutoffs, we want 95% of our values, or this interval, to capture 95% of the bulk of values in that distribution. All right, and that means we have 5% in the tails. Each tail then is going to have 2.5%, and we're symmetric. Right? We're mirror images. So for that, do it like this, just like we had in the presentation. Gives us negative 2.57 and positive 2.57. They're the same value. One's positive, one's negative. And they're the same value for a reason. We're mirror images. All right? And we have the same percentage, 2.5%, in each tail. All right? This is normal. Now we're going to do that because if we're going to use it to calculate a confidence interval, we're going to say mean plus our t times the standard error. Since this is a vector of two values, it'll give us the lower and the upper bound of our confidence intervals, no problem. 90%, 99% cutoffs. Now we want our interval to capture 99% of all of the values. That's going to capture the bulk, which means our tails only have 1%. That's 0.5% in each of our tails. So here is our vector of probabilities, or a vector of quantiles. We want 0.5% on the left, and then we want 0.5% on the right, but since we're doing lower dot tail equals t, we're actually using 0.995. 99.5 all the way to the left of our point. And again, degrees of freedom, I said arbitrarily use df equals 5. Maybe it's 10, maybe it's 20, who knows. But these are the values. So for 5 degrees of freedom, our lower value is negative 4.03, our positive value is positive, or our upper value is positive 4.03. Then our 90% cutoff. Again, we've got 90%, that's our bulk, which means we have 10% in the tails. Each tail then has 5% of our values. Same thing, we get negative 2.015, positive 2.015. Okay, this is an R. We can also use a table. So, on Blackboard, I have a t-table that's posted. I believe it's this one. I should probably check it. Students' t distribution. And actually, I think that's what we're going to do. Let me move that over. We are going to check it real quick. This is also one of those where you can look up a t-table and you're going to find many different t-tables on the internet. They all have the same information. All right? They all have the same information. So, statistical tables, t-table, table B. All right, so I've got a different table. So this is the table that's up. Let me open that one instead. T-table, table B. Rotate. There we go. All right. This is from Sokol and Rolf. This is critical values of the t-distribution. What is important is what it gives us. So in the book, it tells us what area it's giving us. So it's going to give us the tails. That's what we're focused on. It's arranged as we have our alpha up top here. So this alpha is telling us percentage of values that are in the tails. And this is the percentage of value in both of our tails. All right? This is a percentage of values in both of our tails. V, or nu here, is our degrees of freedom. So what we can do, we've already done this. We know what we're looking for. 5 degrees of freedom. We wanted a 95% confidence interval, right? 2.57. That's our value. And then it's going to be negative 2.57 if we're on the left. It'll be positive 2.57 if we're up on the right. All right? We did a 99% confidence interval, right? 4.032. There it is. So 99% corresponds to 1% in our tails. We just read right down the column to get to that degrees of freedom. And then we did a 90%, that's 10% in the tails, and we get 2.015. All right? Pretty easy, right? Using R, using the table, do what you want. We just need to make sure that you're using a table that is technically a two-tailed table. So these percentages, these alphas, are the percentages in both of our tails together, not individually. All right. Any questions? Any questions? Easy? So far, so good? All right, so these are what I call critical values. And I call them critical values because when we do our t-test, you're going to see that our p-value gets compared to a critical value. Or actually, in R, it'll actually give us the area under the curve. But if we did it by hand, we needed to know what our critical value is. So we already did 95, 98, 99, and 90 for all 1 degrees of freedom. You can try these with various degrees of freedom and see what you get. What I would do is do it in R, since we have code that does it with the degrees of freedom. Just change your degrees of freedom, and then see if you can find that same number using the table, just to confirm. If you were doing it by hand, we definitely do some of these on the table. All right, so we use those values to get our confidence interval. All right, so we're going to use our t cutoff values. And we're going to multiply that t value by the standard error of our sample. And that's going to give us our plus and minus value of the mean. So then for our confidence interval, we're going to be below our mean and above our mean that certain amount. So here's an example of how we would do it. And I'm going to do this on the board, kind of write it out on the board so you can see it. So we have 20 raccoons. The mean is 23. The variance is 2.5. We want to calculate the 95% confidence interval of the mean. All right, we want to calculate the 95% confidence interval of the mean, and then we want to interpret it. So we've already done our t value. So we wanted 95%, right? We wanted 95%. So that means our t, 95% value, which is 0.05, that's our alpha. And degrees of freedom is, what's our degrees of freedom? 19. All right, so we're going to need that value. All right, we're going to need this value. So go ahead and figure out what that value is with our new degrees of freedom. You could use the table or you can use R. It's up to you. Where did that go? Seem to have lost it. Lost it. Get some of this stuff back. Oh, it's like going off the screen. All right, so what's our t value here? 19 degrees of freedom. We wanted 95%. What'd you get, Cody?
Negative 2.493.
All right, so it's going to be a plus or minus. It's going to be a negative. It's going to be a plus. And that's one of the reasons why we have mean plus or minus, because it's going to correspond to the plus or minus of our t. So that's going to be our t. All right. We need our standard error. Our standard error is our standard deviation over the square root of our sample size, right? So we actually have a variance, and that's 2.5. All right, 2.5. Our sample size is 20. All right. Well, we don't want the variance. We actually want our standard deviation. So we're going to have to take the square root of our standard deviation in order to get our standard error. And then once we have that, we can divide it by the square root of our sample size. So what do we get for our standard error? What you get?
354.
Yep, 0.354. That's what I got. All right. So now what we have to do is get our actual confidence interval. So this is a 95% confidence interval. This will be our mean, which is 23.0, plus or minus our t value, 2.093, times our standard error, 0.354. All right. So calculate that. Let's get our range. Is that the range that you got? 22.26 to 23.74? Right? All right, so interpret that range. What does this mean? What does this mean? Verbalize. Anybody? Verbalize it? This range here, 22.26 to 23.74. We are 95% confident that this range captures our true mean. That mu falls someplace between this, or not falls, gets captured by this range. If we repeated the sample, collected 20 more raccoons, all right, yeah, our range is going to change because our mean changes, our variance changes. But 95% of all of our confidence intervals are going to capture that true mean. That's what our confidence intervals are telling us. All right, so second example. Generate a random sample of 50 points drawn from a normal 50,2 distribution. So this is how I did it, all right? And when I did it for this presentation, there it is. When I did it for this presentation, these are the values that I got, okay? We want to calculate 95% confidence interval. So use R, generate your Rx vector, all right? Calculate the mean of that Rx vector, calculate the standard error of that Rx value, and then do your 95% confidence interval. Everyone's going to have a different interval, all right? But what we want to see is we have, here in the class right now, we have 13, including myself and those at home, right? If we're right, basically all of us, with the exception of maybe one person, will have a confidence interval that does not capture the true mean, which is 50. All right? So give you some time. I'm going to get this going on my side, so we'll try. And it's 50 data points. So 50, that's what we're going to do, 50 data points. Will got close with his answer. Not that the value lies within that interval, because the lying implies that our value, that mu can change, but mu can't. So it's better to say that our interval captures that mu. And you're going to see it because we can use these confidence intervals as like a one sample test. So we can ask, is our sample mean actually equal to 50? And if our confidence interval includes the value 50, and a 95% confidence interval, if it includes that value 50, then we conclude, yes, our sample mean is equal to that value. It's part of our hypothesis. Did you get it? Everyone's is going to be different. Did you get the standard error working? Maybe? Yes? No? So, here's mine. All right, so I generated my random normal vector, Rx. I already had it generated. I'm going to go ahead and run it again, get a new set of numbers. All right, everyone should have this. We called it Rx, just a random x variable. All right, so then the 95% confidence interval, I actually did it all in one line. Because we know the equation. It's going to be our mean of that vector, and then it's going to be plus our QT value, the cutoff values, times our standard error of that vector. All right, so instead of doing everything separately, I did it all in one line. So this gives us our cutoff values. That's going to give us a plus, and it's going to give us a minus. It's going to give us two values, whereas mean and standard error is only one. So when we do this, we're going to have a negative value, and then we're going to have a positive value. Now, with the QT, we want a 95% confidence interval, so that vector is 0.025 and 0.975. 2.5% in each tail, which gives us 95% in the bulk of our distribution. For the degrees of freedom, it's going to be our sample size minus 1. Well, I know it's 50, right? I know we have a sample size of 50. And then we would do 50 minus 1 to give us 49. That works. Or I just use length of our vector minus 1. That also gives us our sample size minus 1. And then lower dot tail equals t, because that's going to be standard for us at this point. All right, and then we multiply that QT value by the standard error. And remember, we introduced that standard error function on Monday. So I'm going to make use of it here. STERR of that Rx vector. And when I run it, I get a plus and minus. I go to lower bound and an upper bound. So for this data set, for my sample, my random sample, my 95% confidence interval is 49.4 up to 50.5. So how many of you have an interval that actually includes 50? How many of you have an interval that does not include 50? What was yours?
I got 49.0018 to 49.889.
Okay, so we are just shy of 50, right? And that's a confidence interval. And we're just demonstrating that this is what's happening. Our population mean did not change. It is 50. But we drew a random sample, and our sample averages are going to change based on our sample. And just in this class, we have 13 here. I don't know how many are actually following along live at home. All right. I don't know how many of that. 6 are saying they're watching right now, but we have a couple playbacks, so probably pauses and whatnot. But that demonstrates that if we did this, if we had 100 people do this exact same thing, we estimate 5 of them will have a confidence interval that does not include 50. Because it's our sample values that change, not the population mean. Population stays at 50. So that's the meaning of our confidence intervals. Questions? Did you get this? Did you get your intervals? Yes?
I have a very basic question.
Okay, very basic question.
Yeah, I'm going over my head right now. But, for example, how did we get 19 degrees of freedom? Did I miss that? Oh, this is minus one, okay. See?
Yep, sample size minus 1. How did you get 19 degrees of freedom? Sample size minus 1. So this is why we had 50 samples,
Got it.
right? We did 50 minus 1. So yeah, 95% of all of our confidence intervals should capture 50. That's what it is. All right, so I do have up on here where I showed the actual work. Make sure we can see that. Yep. So this is what we did up on the board. So you can see, you know, the same sort of thing. All right, if we were going to do it by hand, I also had how we do it by hand, but we showed you how to do it in R. All right, so how do we improve our confidence intervals? Really, it all comes down to this, standard error. All right, if we look at our confidence interval and we say, oh, it's way too wide, you know, it's 49 to 51, and I need it to be 49.5 to 50.5. All right, how do we do that? Well, it comes down to our standard error. All right, ways we can decrease that length is decrease the standard deviation. A lot of times you don't have any control over that, unless it's measurement error. Right? If it's measurement error, if it's us who's making that error, yeah, we can fix that. But normally we can't do anything about that. The other way is to increase your sample size. So instead of measuring 20 raccoon, maybe measure 40 or 50. That's going to have the same effect. Not only is it decreasing the standard error, because if you increase the denominator, you decrease the standard error, but it's also increasing the degrees of freedom. And with our T table, I said, as we increased our degrees of freedom, we approached normality. So as our confidence intervals increased, here it is. This is the column, the 95% column that we would use. You can see as our degrees of freedom increase, we get closer and closer and closer to 1.96. That 1.96 is your 95% cutoff of a normal distribution. So an infinitely large population size, we do basically follow the normal distribution. Increase the sample size, our t-value gets smaller, decreases your confidence interval. All right, so we're going to end here for today. Looking ahead, we're going to get to how do we report the error, right? So this is kind of the rounding, standard error, rounding of confidence intervals. We'll give you some rules on that, and then we're going to be moving to these one sample tests. Is our population, is our sample average equal to some value? Right? And this will be our first foray into a hypothesis test. All right. Y'all have a good one. If you have questions, please email me. And I know there is a homework assignment coming up. It's to do confidence intervals and standard error, and it has the rounding on it. So I'll double check and get those posted. Rebecca, don't close your R stuff yet. Okay?